Hello, everybody, and welcome to this lecture on ocean water. So before we begin, I'm just going to do a little demonstration for you in the lab. What I have here is just a graduated cylinder filled with some salt water and just normal HEB salt I added to this, so I can put in a little bit more just to kind of top it off. So as you know, you're going to hear later in the lecture that, of course, the ocean water has salt in it, has 3.5% salt or 35 per mil salt. Same thing, you'll learn about that in a little bit. So there's my salt water right there. It's a little bit cloudy because you can see that the salt water is, the salt's kind of still hasn't totally dissolved, so it's sort of floating in there. But what I'm going to do is I'm going to add a little bit of fresh water. So I took the fresh water, I made it blue, just to kind of tell the difference. And I'm going to just kind of slowly add that to my salt water. And of course what you see is that the fresh water is suspended on top, right? So you can see the fresh water sits on top of the salt water. Why does it do that? It's because the salt water is denser, right? So denser liquids are going to tend to sink, less dense liquids are going to tend to float. So we're going to go back to this principle again and again and again during the lecture. And what's pretty cool is that when we do this in like our actual face-to-face classes, I keep this graduated cylinder out and it will stay like this for the entire semester. So the salt water and fresh water will never mix. So anyway, just something for you to remember as we continue through this lecture, that saltier water tends to sink, fresher water tends to float. Okay, thank you for listening. Hello everyone, welcome to your lecture on ocean water. This is lecture number 15. And going along with it, I hope you got your book right there, your assigned reading. We're reading chapter 16 in your book, looks like that. So anyway, you want to be following along with your assigned reading that goes with your class and your lectures. Anyway, we are going to be talking about ocean water today. I hope you enjoyed the little demo that we started off with. And got our first question that comes up on the lecture assignment, number 15. Of course, I don't have a physical one, but I see it up here on my screen. It says, how many grams of sea salt are there in the ocean water? So we are going to be talking about ocean water today. That's what we're focusing on. Now, you know that, of course, there's salt in the ocean. Shouldn't come as any surprise to you because probably you're living here on the Gulf Coast. And that salinity is very important to know for this class. The average salinity in the ocean is, there's a lot of different ways to express it. It's 3.5% by weight. So that means that if you have 1,000 grams of water, of seawater, there's going to be 35 grams of salt. That's another way of putting it. So 1,000 grams or 1 kg, right? 1 kg of salt water, seawater, I should say. You're going to have 35 grams of salt dissolved in it, okay? Another way of saying that is 3.5%. Yet another way of saying that is this kind of weird way that you'll see throughout this lecture. In fact, you see it on this slide. It's 35, and it has a weird thing that looks like this, 35 per mil. And you know that this is per mil is instead of percent, means per 100, like per 100 units. Per mil means per 1,000 units. Okay, so another way of saying the amount of salt in the ocean water is per mil, and it's 35 per mil. Another way of saying it is 3.5%. Another way of saying it is 35 grams per kg or per 1,000 grams of ocean water. Okay, so that's the average amount of salt in the ocean, and that's how you should know all three of those ways of expressing it. Okay, so I just answered number 1 and 2, right? And we're going to answer number 3 right now. So what is that salt composed of? Probably you can guess that a lot of it is basically table salt, right? That's why we put sea salt. I'm sure you've seen things like these guys right here are like collecting sea salt. I'm sure you've put sea salt on your food, but I mean salt you buy from the store. it's sodium chloride, right? So it should come as no surprise that sodium chloride, table salt, is the #1 salt that is in the ocean water, okay? But it's not just table salt. There's other stuff in there. So of that 35 grams, that is the total salt dissolved in the ocean water. 19 is from the chloride, and 10 grams, or maybe 11 grams, is from the salt. So you can see that what's 11 plus 19? It's 30. So 30 of the 35 grams of the salt that's in the ocean, that is just sodium chloride, just table salt. Okay. There's other stuff though. Okay. Another one is magnesium and sulfate. In case you don't know what magnesium sulfate is, actually probably you have heard of this before. Magnesium sulfate is Epsom salt. Epsom salt. So it's the same salt that you like, especially like athletes will soak their muscles in, and things like take like a hot bath, things like that. Another thing that it's used for is a laxative. So it's kind of funny because when people are doing this kind of work where they're actually evaporating sea salt to produce salt to actually eat, they have to be very careful to remove the magnesium sulfate, because otherwise you're going to have a terrible laxative effect, right? So you don't want that. But anyway, the 4 most prominent ions composing salt in the ocean, those ions are chloride, sodium, sulfate, magnesium. Okay, another way of just saying it's just table salt and Epsom salt. That's basically it. Everything else, there's some calcium, there's some potassium, and then there's a lot of just kind of minor constituents. Basically, everything else is just in that minor constituents box. It's very small. Okay. So that's what's in the ocean, right? And how does that salt get into the ocean? Basically gets there from 2 sources. Comes from, first source is the dissolved load of rivers. So you know that streams, we learned this in the streams lecture. Streams have a dissolved load. That's all the stuff that's dissolved in the ocean, in the stream water, okay? And you might remember that, like for example, when we talked about the weathering lecture, okay, you might remember how like feldspar breaks down. It picks up potassium ion, it picks up silica ion, okay, SiO2, or maybe I should put SiO4. But anyway, it picks up a lot of ions, and those ions end up in the ocean from the stream water that flows into it. Does that mean that stream water is saltier than ocean water? No way, right? No way. Stream water is way fresher than ocean water, but it does provide the salt for the ocean. And the reason that ocean water is saltier is because, in the process of evaporation, the water gets evaporated, but the salt stays behind. So constantly the ocean's evaporating and evaporating, and more stream water comes and fills in that water that evaporated out and makes up for it, but the salt stays behind, right? So there's a process to remove the water, evaporation, but there's not a good process or too many processes to remove the salt. Okay, so don't think that the stream is saltier just because it brings salt into the ocean. That's not true. This ocean's definitely saltier than the streams that bring the salt into it. Okay, second thing are mid-ocean ridges. So also from the lecture on plate tectonics that at mid-ocean ridges there are, actually no, I don't think you've done plate tectonics yet, I'm sorry, but from the ocean floor lecture, last lecture, you know that there's these mid-ocean ridges, right? So at the mid-ocean ridges, there's a lot of hydrothermal activity because there's a lot of volcanism, right? You remember that from the last lecture. There's a lot of volcanism. There's a lot of hydrothermal activity. That means there's a lot of basically hot water springs on the bottom of the ocean, and that hot water picks up a lot of salt, and it emits the salt in these hydrothermal vents around mid-ocean ridges, and we call those things black smokers. So you look at the video up there, you might have seen videos like this from submersibles showing these like big pipes of hydrothermal vents spewing out this looks like black smoke. It's not really smoke, it's all the dissolved material, dissolved ions and precipitating ions that are coming out of these vents. So anyway, that is the source of the salt in the ocean. Okay, now what we're going to do is take a look at how sea salt salinity varies across the surface of the ocean. Okay, Now, it's kind of interesting. You look at a global map like this of surface salinities, and if you look at it, it doesn't necessarily make a lot of sense. It's kind of hard to put the pieces of the puzzle together here, and I'm going to try to explain it to make it make more sense for you. But this is a map, a global map of surface salinity, okay? Now, if you take a look at this, you'll see that the salinity doesn't really vary that much. We have places where the salinity is like 3.1%, and you'll notice that, where's the, like 3.1%? There's some places that are close to, basically close to the continents that are about 3.1%, right? Here's a question for you. Think about it. Why do you think, like really close, kind of hugging the continents, there happens to be a lot of like kind of relatively fresher water? What do you think? I can't obviously hear your answers, but you might guess it has something to do with runoff from the streams of the continents that are flowing into the rivers. So if that's what you're thinking, you're correct. Okay, it has to do with all the streams that are bringing fresh water into the ocean. Okay, so that's one thing that's going to affect sea salt salinity, right? I ask a little bit about some factors. Number 8, I'm asking about some factors that can affect surface salinities. Well, that fresh water that comes up off the continents, that's one factor, right? And that's going to tend to make the area around it relatively fresh. So you can actually see, like here in the Bay of Bengal, that's the Ganges River, right? The reason that the water's relatively fresh, that's the Ganges River bringing in just a ton of water. Right here, the outlet of the Amazon, you can see a little bit of purple right here around the Mississippi River. So that's some of those effects, okay, that you're seeing. You also notice that in the polar regions, especially the North Pole, you see a lot of relatively fresh water. We'll talk why about that later. Now, if you look at the other end of the spectrum, you see that the salinity can get up to 3.9, actually get higher than that, but on average, it's 3.9 is about as high as it gets, okay? And that's kind of crazy. You think about it, really the surface salinity doesn't change that much between 3.1 and 3.9, okay? Average is, of course, you can see right smack dab in the middle, 3.5%, okay? Where is it really salty? You can see these patches of salt right here and right here, okay? You can also see there's a lot of saltiness in the Mediterranean, in these gulfs, the Persian Gulf and the Red Sea. There's a lot kind of higher salinity. We're going to talk a little bit later about why that is, okay? But you can see these little patches of salinity. And notice that, okay, here's the equator right here, right? You'll notice along the equator, basically it's relatively fresh. It's kind of fresher water, lower salinity. And then in the tropics, I'm going to draw the tropic lines right here. See these little notches right here? Those are the tropic lines. You can see around the tropics, it actually has kind of higher salinity. So we'll explain why that is in just a bit. Okay. So precipitation of the ocean makes the surface water less salty, makes it fresher because it dilutes the salt water. So number 8 says, what are some factors that affect salinity in the upper ocean? Well, precipitation and evaporation are two of those, or some of those processes. Okay, so you should kind of put, for number 8, put precipitation / evaporation. So those two processes together are going to either raise or lower the salinity. Okay, evaporation is going to tend to raise the salinity. So you know that when water is evaporating off, like if I took some salt water here and put it over a burner, put it over the stove top or something and start boiling the water off, the salt would stay behind. So that's going to tend to make the residual water saltier. Okay, so evaporation is going to tend to raise the salinity level. Precipitation, on the other hand, is going to tend to lower the precipitation level. Okay, now I just want to show you this picture here. This is a map of global precipitation. Okay, notice that around the equator, and by the way, we'll kind of study this more when we talk about like wind patterns and pressure, and we talk about weather and climate later in the class. We're going to understand why this is, but for now, just take it granted that around the equator, we actually get the most precipitation on average, right? So you'll notice that this band of really high precipitation in the equatorial area, okay? So that is why, going back to this map, you could see that around the equator, global salinities are relatively low, right? Why are they so low? It's because there's a lot of precipitation, right? So you look at precipitation map, you can kind of make some correlations and connections here with the salinity map. Okay, so around the equator, there's a lot of precipitation. That's going to lower salinity, surface salinity. Okay, on the flip side, you'll notice that this is a map of evaporation. So you'll notice that around the tropic lines, 23.5 north, there's the tropic line 1, okay? Here's tropic line 23.5 degrees south, okay? There's the Tropic of Capricorn, Tropic of Cancer. You'll notice around those tropic lines, the salinity is higher. And also, this is a map, actually, what you're looking at here is a map of evaporation. So the reason that the salinity is higher around the tropics, it's because evaporation outpaces precipitation. So we get more evaporation in those areas. Okay, so that's what's causing there to be higher salinities around the tropic lines. It's because there's more evaporation in the tropics. Why is that? We're going to learn about that later in the class. I'll give you a little explanation a little bit, but we'll get to that eventually. Number 5 says, what's the halocline? We're going to talk about that in a bit. Number 6 says, and number 7, we're going to talk about all those things just a minute, so just hold off on those. Right now we're just talking about factors that are affecting salinity. All right, another factor that comes into effect here is ice formation and ice melting. So you know that when pure water freezes, okay, it's going to make ice. But what happens when salt water freezes? Have you ever thought of that? What happens if you took some salt water and put it in your freezer? Well, what you would get is you would get ice and the salt would be left behind. So when ice forms, like in the wintertime in the Arctic or Antarctic Circle, what happens? The sea ice forms and the salt is left behind. So what's the effect going to be? It's going to be making the surface water more saltier. Okay, so when ice forms in the winter, it makes it saltier. Okay? So when sea ice forms, it leaves the salt behind. That makes the ocean saltier. Vice versa, when the ice melts during the summer, it's going to make the surface less saline, less salty. Okay? So you might notice, though, kind of interestingly, that the surface salinity around the poles is actually, you would think it would kind of even out, right? Like, okay, in the summer I get it, during the summer it melts, it gets less salty. During the winter, the sea ice forms, it gets more salty. Why doesn't it even out to average? And the reason is this. What we're going to learn in just a minute is that there is no temperature profile through the polar waters. So just like you saw in the demonstration earlier at the beginning of this lecture, the salt water is heavier, so it tends to sink. So the surface salinities here are the fresh water tends to sit on top and the salt water just sinks. Okay, we'll talk a little bit why that doesn't happen as much in the tropics and the equator, but that's why you get these very low surface salinities in the polar regions. Okay, so anyway, those are the causes of variations in ocean surface salinity, right? Runoff from rivers, evaporation, precipitation, sea ice formation, sea ice melting. For number 8, I was just kind of thinking you would put runoff from rivers as one, and then kind of put evaporation, precipitation as kind of one thing, and sea ice formation, sea ice melting as another thing. Okay, because they're kind of two edges of the same sword. By the way, just to kind of let you know, why is there more precipitation at the equator? Why is there more evaporation at the tropics? It has to do with these global convection cycles of air. We're going to talk about this when we talk about like wind and pressure in subsequent lectures. So don't worry about it right now, but I just kind of let you know that's why that happens. Okay. All right. So I did want to talk also about the halocline. So the halocline is the change in the change in salinity with the change in depth. So now we kind of looked at how the surface of the ocean, how the salinity changes with latitude, right? We already looked at that. But we haven't yet talked about how it changes with depth. So that's where the halocline comes in. The halocline is the change in the salinity with the change in depth. All right. You'll notice that at high latitudes, so like in polar regions, okay? We start off less salty, so you can see on the what do you call it, the horizontal axis, we have a scale where you're going like less salty to the left, more salty to the right. So you see that, and of course the vertical axis is depth. So we start going down in the poles. You'll notice that we start off fresher and we get saltier as we go down. We move to the right. Okay. Notice that's not true in the equator or the tropics. We get less salty as we go down, right? So the poles are getting saltier as you go down, and the equator and tropical waters are getting less salty as you go down in depth. Okay? Now that change, again, what's that? We call that change in the salinity with depth the halocline. Okay, halo, haline, halite, that all refers to salt. Cline is like an incline, like a slope. So you can see that all three of these things are slopes, right? So it's just showing the slope of the salinity, okay? All right, so how does salt content, number 6 says, how does salt content vary with latitude in the surface of the ocean, the upper 1,000 meters? You can see that the tropics are saltiest, okay? And you see that here, right? Here's the tropics, okay? The blue line, they're saltiest, they're furthest to the right. The equator is kind of basically average, right? So you see that equator's average, and then you see that the poles, the polar water is kind of less salty, okay? So starting at the equator, it's average, then in the tropics it becomes higher salinity, and then it goes slowly down. Once you get to the poles, it becomes less salty, less saline, okay? Now, how does salt content vary once you're at the deep water? So you're below 3,000 meters. So let's take a look at that. 3,000 meters is down here. And what do you see? You see that all those three lines converge. You see that? They all converge. The blue, the red, the green line, they've all converged, and they're basically the same. What does that tell us? It tells us that oceans are really basically homogeneous. That means there's no difference. They're the same below 3 kilometers. So once you get down to 3 kilometers, the temperature, the density, the salinity, everything else, it's basically all the same. It doesn't matter. There's no latitudinal changes, okay? So globally, you can't tell where you are once you're at 3 kilometers, okay? The polar waters are going to feel just like tropical or equatorial waters once you get down to that depth of 3 kilometers, okay? So that answers number 7. We already answered number 8. Number 9 says, what's the thermocline, right? So let's move on to the thermocline. Thermocline is the temperature version of the halocline. So basically the same thing, except now it's temperature. So the thermocline right here, you can see that it's a little bit easier to understand. If you look at the global map, basically it's hot around the equator. It's a little bit cooler around the tropics, and then it's cold at the poles, just like what you would expect, right? There's nothing really surprising about the temperature profile around the Earth in terms of latitude, right? It's cold at the poles, it's warm in the tropics, it's hot at the equator, just like what you would expect, okay? Now let's look at how the thermocline changes. Right, with depth. Like, how is the temperature changing with depth? That's thermocline. Change in temperature with the change in depth, okay? You can see that at the equator, we have a temperature that's, of course, it's highest, right? It's the highest at the surface, so it's very hot. And then you'll notice that temperature absolutely plummets as you go down into the depths, okay? So as you get down deeper and deeper, the temperature just shoots down, goes down very fast. The tropics are still warm water, but they're less warm, and they go down, albeit more slowly. Part of the reason that the tropics do not decrease in temperature as quickly as the equator is because they have a strong halocline, okay? That halocline, right? The stronger halocline kind of stands in the way of hot and cold waters. It kind of helps them to mix more. So anyway, that's why we see like a less pronounced thermocline in the tropical waters versus the equatorial waters. Now here's a very important point I want you all to pay attention to right now, okay? At the poles, this is the green line. Take a look at that.
there's basically no thermocline. Okay? I want you all to just write that down right now and maybe say it out loud, okay? At the poles, in the Arctic and Antarctic Circle, there's no thermocline. There's no temperature profile. There's no change in the temperature with the depth, okay? So we have some questions here. It says, how does surface water temperature vary with latitude? Very obvious. It's what you would expect. It's hot at the equator, a little bit cooler at the tropics, very cold at the poles, okay? How does ocean water temperature vary with latitude at depth? Well, take a look. It's the same story as the halocline, right? Once you get down to 3,000 kilometers depth, there's no temperature change. There's no temperature difference of latitude. So that means if you're in the polar waters at 3,000 kilometers, 3 kilometers depth, versus you're in the equatorial waters at 3 kilometers depth, there's no difference. Okay, you can't tell the difference. All right, it's cold at the equator. It's cold at the poles once you're at that depth. Why? What heats up the ocean? It's the sun. The sun is coming from up top. So once you get down to that depth, it's cold water, no matter where you are. All right, number 12 says, how does surface ocean water density vary with latitude? How does surface ocean water density vary with latitude? So that means we have to take a little look at the density map. Okay, so here's a map of seawater density. And what do you see? Well, it's basically pretty easy to understand. Around the equator, the density is lower. Why is it lower? It's because the water's warmer, right? So you know that as temperature increases, density goes down, okay? So dense water is cold water, hot water is more buoyant water, okay? So density goes, and how does it change with salinity, right? Density goes up with salinity, okay? So density goes up with salinity, it goes down with the temperature, okay? So there's going to be always this kind of like fight between salinity and temperature, okay? So around the equator, you'll notice that generally speaking, the seawater is less dense, and that's due to its salinity is low and its temperature is high, okay? You'll notice places like the Mediterranean. The Mediterranean is going to have pretty high density water. Why does it have high density water? It's because of the salinity is increasing the density there. Okay, you'll notice that around the poles, the density is pretty high. Why is it pretty high? It's because the temperature is low. So to kind of make sense of everything, you kind of have to put the temperature and the salinity maps together. Because like I said, temperature goes up, salinity goes down. I'm sorry, temperature goes up, density goes down. Salinity goes up, density goes up. Okay. Some places like the Dead Sea, it's an inland sea in the Holy Lands or in Israel. The density is very, very high because the salinity is 35%, 10 times higher than what you get in the average ocean. So that's why people can kind of sit here and read a newspaper and just float in the Dead Sea very easily because the water is so dense. Okay. So there you go. There's your map of seawater density again. And of course, temperature is going to be probably the major effect on density, but salinity affects it as well. Okay. Now this change, again, we're going to look at how density changes with depth, right? So how does density of ocean water change with depth? Well, that we call the pycnocline. Okay, so we have a halocline, that's salinity with depth. We have the thermocline, that's temperature with depth. And third thing, we have a pycnocline, that is density changes with depth. Okay, so you'll see that at low latitudes, so that's the equator, we see that we have a pretty heavy pycnocline, right? Okay, we start off at a low density, it's going to get denser as we go down. Why? It's because the decreasing temperature, right? Temperature goes down, it gets colder water, you're going to get denser water. And that all makes sense, right? Because you would expect denser water is going to be on the bottom, right? Less dense water is going to be on top. All right. What about high latitudes? Very important. I've emphasized this already. There's no thermocline, therefore there's no pycnocline, right? There's no pycnocline. It's absent at high latitudes, right? At the poles. At the polar waters, there's no thermocline. There's no pycnocline. Okay. So I hope that you understand now why at the poles salty water just sinks. So as soon as there's ice formation and you make this salty residual water from ice formation in the winter, that salty water is just going to sink. There's nothing stopping it from just going down. Okay? Because when salty water forms in the tropics, it can't just go down and sink down because the thermocline stops it. But in the poles, you have no thermocline, you have no pycnocline, so the salt water immediately sinks down. Okay, so that's why you have relatively fresher water at the surface. All right. So getting on to number 15, we have a question here. What is heat capacity? Does water have a relatively high heat capacity, a relatively low heat capacity? So heat capacity of water is insanely high. If you compare it to, in fact, I could actually bring up, just kind of show you. I don't have the slide here, but I should show you this slide. Heat capacity of water compared. You would see that it really has a very high heat capacity. So if you look at water here, right, water has a heat capacity of 4,181 joules per kg per Kelvin. I guess helium has a higher one, but it's really insanely high compared to things like glass, diamond, concrete, aluminum. It's comparing it to different things. And you could see that water is right on top. Here's 4.18. It's just, it's the same thing. Heat capacity of liquid water is a lot higher than anything else, right? So water just has an insanely high heat capacity, okay? What is heat capacity? It's how much energy it takes to change the temperature of something, okay? How much energy it takes to change the temperature of something. So it takes a lot of energy to change the temperature of water. That's why, for example, coastal places like Corpus Christi have kind of a more even temperature profile throughout the year. So actually, we'll do this a little bit later in the class. We'll look at the climate in Corpus Christi compared to San Antonio. And what you see is that Corpus Christi, which is a coastal city, has cooler summers and it has warmer winters than San Antonio does. Why is that? It's because we're coastal. We're on the coast. We're close to the ocean. And that explains why, for example, I'm showing up here Chicago, Illinois versus Seattle, Washington. Now, Chicago, Illinois is inland. Of course, it's actually on the coast of Lake Michigan, but we're not counting Lake Michigan. But it's inland. It's inside the country. Versus Seattle is coastal. It's marine, coastal, west coast of our country. So you'll notice that it gets a lot hotter in Chicago in the summer than it does in Seattle, Washington, and it gets a lot colder in the winter in Chicago than it does in Seattle, Washington. So it's more extreme temperatures. And the same thing with San Antonio. We could do the same thing. In fact, we will do the same thing later with Corpus Christi versus San Antonio. Even though San Antonio is pretty close by, 2 hours away, 2.5 hours away, we have a different temperature profile. We have a warmer winter here in Corpus, and we have a cooler summer. Okay, so that's because we're coastal, and it's because the water has a high heat capacity. It takes a lot of energy to change the temperature of water. Okay, so now we're getting on to number 16. We covered that. Another thing we want to talk about is the thermal expansivity of water. So what does thermal expansivity mean? Well, you might know that when the temperatures of some materials change, their volume changes as well. That's why, for example, maybe, I don't know if any of you have never noticed this. Sometimes I talked about this with students and they've never noticed this, but you might notice that at certain times of day, you'll kind of hear your house creaking, and it's because it's cooling off or it's warming up. And the wood, or something that a lot of people do notice, is that during the summer, they'll have a door that doesn't stick, but then in the winter, that door will start to stick, or that cupboard will start to stick. And it's because the materials of your house are expanding and contracting with the temperature changes, okay? Well, water does the same thing. It expands or it contracts according to the temperature, okay? So that's why, for example, when it comes to things like sea level rise, it's not just a matter of extra water coming into the ocean from glaciers that might be melting off. That's part of it. But there's another part of it, is that the water itself is expanding as it heats up. So, for example, if you were to take a column of water, and the average depth we learned of water is about 4,500 meters, right? So let's say take a 5,000 meter column of water, and you increase the temperature by 1 degree. Just increasing it by 1 degree, of course, that would be a huge amount of energy it takes to change the temperature of the ocean by 1 degree, but that would result in 26 centimeters of sea level rise just from the thermal expansion of the water. Okay. Sea level rise is incredibly complicated. We talk about this in oceanography, and it's just the small part of the story, but I just want you to be aware of things like that. Okay. Another thing I want to talk about is acidity. So, we've learned in this class already that as CO2 dissolves into water, what happens to the water? It forms carbonic acid. And when carbonic acid forms, it can change the pH of the ocean. Now, things are complicated in the ocean because the ocean's actually acidically buffered. So there's a lot of things that kind of keep the pH in check. So a lot of CO2 can actually dissolve into the ocean without changing the pH too much. Nevertheless, with CO2 levels slowly creeping up, we do get changes in ocean surface acidity. So these are changes in pH that we've seen over time. And you can see they're not big changes, right? You're talking about changes that are ranging from, from 0 to all the way to like 0.1, right? So they're not huge changes to the pH, but they are. They do have effects. So you have to remember that a lot of marine organisms, we've already learned in this class, a lot of marine organisms make their shells out of calcite or aragonite or some kind of calcium carbonate. And you might remember that calcium carbonate will break down and form CO2 once you react it with acid, right? So as water becomes more acidic, it makes it more difficult for these little organisms that make their shells out of CO2. Coral, for example, makes its skeleton out of CO2. It makes it more difficult for them to secrete their calcium carbonate skeletons and therefore live, right? So that's why you have things like coral bleaching. That's where the coral, when you say coral bleaching, it just means the coral's died, right? The coral animal has died. And it's sensitive to ocean pH, right? So that's why we have a concern about it. But anyway, that's all we have. I think we covered everything that's on your lecture assignment up to number 18. So hope you enjoyed the lecture. I'll talk to you next time, and have a good week.